Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Our deep dive today is really fundamental. We're talking thermodynamics, material properties, and how they connect to managing energy and, importantly, pollution. This is the stuff you absolutely need to know, sort of the bedrock for talking shop with any engineer.
Exactly. That's the mission today. We've looked at the core sources,
Mhm.
property tables, the energy laws, even specific pollution control tech. We want to pull it all together, make it clear how these basic physics concepts drive, well, pretty much every design choice. From pumps to scrubbers.
Okay, let's dive in. Thermodynamics. It all started way back with Sadi Carnot trying to figure out the motive power of fire. It's a huge field, but really rests on two key ideas. Let's start with the first law.
Right. The first law, it's like the universe's accountant. It's all about conserving energy. Basically, it says the change in a system's total energy, that's E2 minus E1, has to equal the heat you add minus the work the system does. Simple balance.
So energy itself, that's a property of the system, depends only on its state.
Precisely. That's the critical point. Energy is a state property. But heat transfer delta Q and work transfer delta W, those aren't properties. They depend on how you get from state 1 to state 2. They're path-dependent interactions.
Okay. And that total energy change, E2 minus E1, what goes into that?
Well, it breaks down into three main parts. The change in internal energy, which is U2 minus U1, plus the change in kinetic energy. That's 1/2 m times the difference V2 squared minus V1 squared. And then plus the change in gravitational potential energy, mg times Z2 minus Z1. The first law just makes sure we track it all.
Got it. So
Yeah.
the first law says energy is conserved. What about the second law? That one feels different, more restrictive.
Yeah, you could say that. The second law introduces the concept of irreversibility. It's sort of the universe's tax, the cost of doing anything useful. It tells us we can't ever perfectly convert heat to work or run processes backward without some loss.
And we quantify this loss, this irreversibility.
We do, using entropy generation. We call it SGen. For any real process in a closed system, SGen has to be greater than or equal to 0. Mathematically, SGen equals S2 minus S1 minus the integral from 1 to 2 of delta Q divided by T, and that whole thing is greater than or equal to 0. 0 means perfectly reversible, which, never actually happens. Positive means you've generated some irreversibility, some waste.
Okay, here's the thing, though. Engineers talk about efficiency constantly. How does this abstract entropy generation connect to, well, lost work, lost money?
That's the crucial link. It's formalized by the Gauss-Stodel theorem. This is like the ultimate practical consequence of the second law for engineers. It tells you exactly how much useful work potential you've thrown away.
Okay, break that down.
The rate of lost work, let's call it W lost, is directly proportional to the rate of entropy generation, S dot gen. The equation is just W lost equals T0 times S dot gen. T0 there is the absolute temperature of the surroundings, your environment.
Wow. So minimizing that S dot gen is literally minimizing the work you could have gotten but didn't.
Exactly. Think of entropy generation as the friction or the heat leak in your process, and Gauss-Stodel puts a price tag on it in terms of lost work. So if you want the most efficient system, your design goal number 1 has to be minimizing entropy generation, period.
Okay, that makes sense. So we have these fundamental laws. How do they apply when we're dealing with actual stuff, the working fluids in engines or refrigerators? We often use simplified models for these substances, right?
We do, because real substance behavior can be incredibly complex. The two workhorse models are the ideal gas and the incompressible substance. They represent opposite ends of the spectrum.
Let's start with ideal gases. When does that model work well?
It's great for gases at high temperatures and relatively low pressures. Think air in an engine cylinder before combustion or hot exhaust gases. The defining relationship is beautifully simple. Pressure P times specific volume V equals R times T. Well, actually just PV equals R times T. Well, actually just PV equals R constant, where R is the ideal gas constant for that specific gas.
Right, the ideal gas law. And with ideal gases, specific heats become important.
Well, very important. We use C sub P, the specific heat at constant pressure, and C sub V, specific heat at constant volume. And for an ideal gas, they have a simple relationship. C sub P equals C sub V plus R, that same gas constant.
Do you have a number for R, say for air?
Yep, for air, R is about 286.8 joules per kilogram per Kelvin. Knowing R, Cp, and Cv lets us easily calculate changes in internal energy and enthalpy for ideal gases.
Okay, what about the other extreme? Liquids and solids.
There, we often use the incompressible substance model. Think water in a pump or a block of metal. The key assumption is constant density. This usually holds well at high pressures or low temperatures, basically when the substance isn't easily squished.
And how does that simplify things?
It simplifies the specific heats dramatically. For an incompressible substance, C sub P and C sub V are essentially the same. So we just talk about the specific heat, C. So C equals C sub V, which approximately equals C sub B, makes calculations much easier.
Now, you mentioned internal energy and enthalpy, and entropy came up with the second law. These aren't always easy to measure directly. How do we relate them back to things we can measure, like pressure and temperature?
Good question. We use what are called derived thermodynamic property relations. These are mathematically derived equations that link different properties together. A really important one involves Gibbs free energy, denoted by G. Its change, dG, can be expressed as dG equals minus SdT plus VdP.
Okay, unpack that. STVP.
Right, so S is specific entropy, T is temperature, V is specific volume, and P is pressure. What's powerful about this equation is it shows how changes in entropy, S, and volume V, are directly related to changes in measurable things, temperature, T, and pressure, P. Relationships like this are actually how thermodynamic property tables, those big books of data, are constructed from experimental measurement.
Speaking of measurements, units, a classic engineering pitfall. We use SI units mostly, but conversions still bite people. Any key ones to remember?
Oh, definitely. Pressure is a big one. 1 bar is exactly 10 to the power of 5 pascals. Don't forget that. And if you're dealing with older systems or U.S. customary units, that's roughly 14.504 pounds per square inch, absolute size IA. Mixing those up causes huge errors.
Yeah, I can imagine. What about temperature? Kelvin versus Celsius.
The key thing to remember is that temperature differences are the same in Kelvin and Celsius. So a change, delta T, of, say, 10 degrees Celsius is exactly the same as a delta T of 10 Kelvin. Absolute temperatures are different. Kelvin equals Celsius plus 273.15, but the change is identical, critical for heat transfer calcs.
Right. Okay, so now we have the laws and models for substances. Let's apply them to actual engineering components. Turbines, compressors, these are usually open systems with stuff flowing through, right?
Exactly. We analyze them using a control volume approach, looking at what crosses the boundary. Steady flow is a common assumption. Let's take a turbine first. Its job is to produce work.
Okay, so fluid flows in, expands, spins the turbine, flows out. How do we calculate the work?
The work rate, W dot T, coming out is simply the mass flow rate, N dot, times the change in specific enthalpy from inlet to outlet. So M dot out times H1 minus H2. Enthalpy drops, work comes out.
And efficiency. How good is the turbine at doing that?
We use the first law of efficiency, often called isentropic efficiency for turbines. A dot T, it's the ratio of the actual enthalpy drop, H1 minus H2, divided by the ideal enthalpy drop you'd get if the process were reversible, meaning isentropic, H1 minus H2S.
The S means constant entropy.
Yes, H2S is the enthalpy at the exit pressure. If the entropy stayed the same as the inlet entropy, S1, it represents the maximum possible work extraction according to the second law. And the second law also tells us directly that the entropy generation rate, S dot gen, which equals M dot dot times S2 minus S1, must be greater than or equal to 0 for the real turbine.
Okay, now flip it. Compressors or pumps, they consume work to increase pressure.
Right. The required work rate input, W dot C, is M dot dot times the enthalpy increase, H2 minus H1.
And the efficiency definition. It must be different, right?
It is. It's flipped upside down compared to the turbine. Compressor efficiency, A to C, is the ideal reversible work required divided by the actual work required. So it's H2S minus H1 divided by H2 minus H1.
Why the flip? Why is the ideal the numerator here?
Because the ideal reversible process represents the minimum work needed to achieve that pressure rise. Any irreversibility friction, heat transfer, means you have to put more work in to get the same result.
Ah, okay. So a real compressor always needs more work than the ideal one.
Exactly. And again, the second law confirms this. S dot gen equals M dot dot times S2 minus S1. And this must be greater than 0 for any real compressor or pump. That generated entropy is why you need the extra work input compared to the ideal case. It directly connects back to lost work, just like Geuss said.
This is great. It really ties the fundamentals to component performance. Now let's shift gears a bit and connect this to the environment. Pollution control. Combustion is central to so much mechanical engineering, but it's a major source of pollution. Stationary sources, like power plants, are big contributors, right?
Huge, especially for sulfur dioxide, SO2, and oxides of nitrogen, NOx. You mentioned the stats like 91% of US SO2 and half the NOx comes from stationary combustion.
So how do we deal with SO2 after it's formed?
The main technology is flue gas desulfurization, or FGD scrubbers, basically. The most common type is a wet scrubber. You use a slurry, usually lime or limestone in water, to absorb the SO2 from the flue gas.
And they work well.
Very well. Efficiencies are typically high, often 90% or even better.
But I imagine handling that wet sludge afterwards is a headache.
It absolutely is. It adds cost, complexity, disposal issues, which leads to the alternative. Dry scrubbers, or often called spray dryer absorbers, SDAs. Here you spray a finer slurry into the hot gas, the water evaporates quickly, the SO2 reacts, and you're left with a dry powder waste product.
Easier to handle, I assume.
Generally, yes. Lower capital and operating costs often, but the trade-off is usually efficiency. SDAs typically run in the 70 to 90% removal range, not quite as good as the best wet scrubbers.
So there's that trade-off again. Higher efficiency might mean more complex waste handling, a higher cost in a different way. It's an optimization problem.
Exactly. It's rarely just about maximizing the thermodynamic efficiency of the separation itself. You have to consider the whole system cost and impact, including waste disposal. Sometimes accepting slightly higher entropy generation in the scrubber itself is worth it if it drastically reduces the entropy and cost of dealing with the byproduct.
Makes sense. What about NOx control? Oxides of nitrogen, you said prevention is key there.
Yeah, because once NO is formed especially, it's much harder to scrub out chemically than SO2. The main culprit is thermal NOx. This forms when the nitrogen and oxygen that are just naturally present in the combustion air get really hot in the flame, they react.
And the reaction depends heavily on temperature.
Exponentially. Higher peak flame temperature means much more thermal NOx.
So the solution is cooler flames.
Essentially, yes. That's the principle behind low NOx burners, or LNBs. They're designed to carefully control how the fuel and air mix. They stage the combustion, create fuel-rich zones initially, and manage airflow to reduce those peak flame temperatures. They also limit how much oxygen is available right in the hottest zones. It's clever fluid dynamics and reaction control.
Okay, so we've covered air pollution from combustion. What about water pollution? Similar principles apply.
Absolutely. Separation processes are key. For municipal wastewater treatment, the basic goals are usually set by regulations. Typically, they need to reduce BOD, biochemical oxygen demand, basically how much oxygen microbes will consume to break down the waste and suspended solids, SS, by at least 85%, or meet specific effluent limits, often around 30 milligrams per liter for both BOD and SS.
And beyond standard biological treatment, what advanced methods use these thermodynamic or separation principles?
Well, activated carbon adsorption is a big one. It's used to remove dissolved organic compounds, things like benzene, solvents that biological treatment might miss. You pass the water through columns packed with granular activated carbon. The organics stick to the surface of the carbon.
How do you know how much carbon you need, how much it can hold?
We model the capacity using adsorption isotherms. A common one is the Freundlich isotherm. It relates the amount adsorbed per unit mass of carbon, Q, to the concentration of the solute in the water, C. The equation looks like Q equals K1 times C to the power of 1 over N. K1 and N are constants determined experimentally for a specific pollutant and carbon type. The key thing is it's non-linear. Capacity doesn't just scale directly with concentration.
Interesting. So you need data to design it properly. What about removing salts, inorganic ions?
For that, membrane technologies are dominant. Reverse osmosis, or RO, is probably the most widespread for desalination and high-purity water. You use very high pressure, sometimes hundreds of psi's, to literally force water molecules through a semi-permeable membrane, leaving salts and other solutes behind.
That high pressure sounds like a lot of work input. Back to thermodynamics.
Directly. You're expending work via the pump to overcome the osmotic pressure, which is related to the chemical potential difference between the fresh water and the salty water. It's the energy cost of separation.
Is there an alternative to RO for ion removal?
Yes, electrodialysis, or ED. It also uses membranes, but specialized ones that allow ions to pass, not water. You apply a direct electric current across the stack. Cations, positive ions, move towards the cathode. Anions, negative ions, towards the anode, passing through their respective membranes, leaving purified water in the central channel. So instead of pressure work, you're using electrical work to achieve the separation. Different driving force, same thermodynamic principle of needing energy input to create order. Separation.
Wow. Okay. So from Carnot's original questions about fire all the way to designing membrane systems for pure water, it really all comes back to these core thermodynamic laws.
It absolutely does. The first law tracks the energy, but the second law, through entropy generation and lost work, dictates the efficiency, the cost, the feasibility of everything. From how much work a turbine produces to how much energy a desalination plant consumes, to the trade-offs in designing a pollution scrubber. The constant challenge is minimizing that irreversible entropy generation within the economic and practical constraints.
So the challenge for you design junkies listening is this. Next time you look at any piece of engineering equipment, any process, ask yourself, where is the available work being lost? What part of the system, what material property, what interaction is generating the most entropy? Finding that is the first step to making it better. Until the next equation, design junkies, we are mechanical engineering made simple.